that you have two recursive calls to merge sort, and those were on arrays of size roughly n over 2. Okay. And we had this merging step which took linear time. Okay. So that was the reasoning why we got this T of n equals 2T of n over 2 plus O of n. And so today's class will basically be about how you obtain closed form solutions. Okay, so that bound is nice, but it doesn't tell you what the actual time complexity is, right? So it only tells you time complexity in terms of it's a recursive bound. Okay, so today we'll try to get like closed form solutions, and we'll see another example of divide and conquer. And as I said last time, this is an example where it's not clear that divide and conquer will be a priori helpful. Okay. And I wanted to point out that so throughout the course, or most of the course, we'll be using lecture notes by Jeff Erickson. Okay, so he's at UC and he has really good lecture notes. Okay, so for most parts, including this first lecture, we'll be using these lecture notes. So in general, because there is no textbook for the class, I will do this. So every time, for every class, basically I'll tell you where you can find notes for it. Okay. All right. So let's see formally today what recurrence relations are. Okay. Show of hand, how many of you have seen how to analyze these recurrence relations before? Okay. So some of you have not seen. So it's the first homework will have a bunch of these things, so you'll get some practice. Okay. So as I'll tell you in a bit, there's no general way of solving these kind of recurrence relations unless they have very simple form. So it's more of a practice kind of a thing. So you do a bunch of them, you'll see a pattern, you'll figure out how to do them. Okay. So the first homework will have one question devoted to this. So alright, so what are recurrence relations? So it's as the name suggests, you have some function, let's say the running time of an algorithm that you want to bound, okay? And you bound it inductively or recursively in terms of the same function but on a smaller size. Okay? So that's what's called a recurrence relation. So an example could be like you could have f of n equals f of n minus 1 plus 2. Okay? So this is a very simple recurrence relation. And here you actually have equality. Okay? So in the first few you have actually equality. You know that f of n is equal to these things. Okay? And you could also just have a bound. Okay? So like in the last but one thing, you just wrote f of n is smaller than or equal to this. Then in such cases, what you're looking for is just something of the form f of n is smaller than or equal to some function of n. So, and you could also have more complicated things. Okay? So you could have f and g, and both of them could be related like this. Okay? And we'll see how to deal with this. Right? So is the, I've defined using examples, but is the kind of the notion clear? Alright. Okay. So how do we solve this? And by solving this I mean obtain bounds or obtain equalities that don't depend on the function value itself. Okay, so how do I get some f of n to be some specific function of n? Like in the first case, turns out to be like 2 times n or something like that. So how do you obtain specific bounds like this? And as I said before, there is no general method for doing this. Okay? So in this sense, it's a little bit like integration, right? So I guess all of you must have seen integration in calculus classes, right? So you have something of the kind, let's say, you have some integral some sine squared x dx, right? Now, how do you solve this integral? Right? So each specific integral has certain specific ways of solving it, right? So you can, if you knew the answer, it's very easy to verify that it's correct. Okay. But actually obtaining this is kind of tricky, right? So you have to try a bunch of things and then you have to do something. Okay. So the same is true for recurrence relations. So if you knew the answer, you can usually prove by induction. Okay, so if you knew the answer, you can usually prove by induction that this bound or this equality holds. Okay, because I mean, after all, what we said is f of n is defined inductively, right? So if you knew an expression, you could prove it by induction. Okay, so this is the thing, and for specific cases, there are theorems. Okay, so there is something called the master theorem. So the name sounds pretty all-encompassing, but it's actually pretty restrictive. Okay, so we'll see how in the homeworks. Actually, one of the homeworks will deal with the proof of this. Okay, from what you see in today's class, it should be easy to prove this theorem. Okay, so okay, but the best thing to do when you see a recurrence relation is you do some heuristic calculation. We'll see how to do these things in today's class. You guess the answer and you prove by induction that this answer is correct. Okay, so it sounds very hand-wavy, but it's usually the best way to deal with recurrences. Okay, so the more you try to structure it, the more annoying it gets, and then there are too many cases to consider, and then you have these complicated-looking theorems. Okay, so it's just easier to do it on a case-by-case basis. Okay. All right. So what do I mean by heuristic calculation? Okay, so today we'll see a bunch of examples. Should hopefully convince you that usually you can try to work out what the answer should be. Okay. So let's take this very simple recurrence relation. F of n equals f of n minus 1 plus 2. Okay. And we'll introduce this notion of what's called a recursion tree. Okay. So this is generally a good notion to keep in mind when you're dealing with recursive algorithms. Okay, so you want to analyze the running time of some recursive algorithm, you try to keep track of this recursion tree. Okay, so what is this? So let's do this simple example. Okay, so you have f of n equals f of n minus 1 plus 2. Okay, so what do you guess is the solution to this? Any guesses? N? Yeah, it's O of n, or it's to be precise, it's something like 2n, right? That's assuming something about f of 1, but let's get there. Okay. So how do you go about formally reasoning about this? So what is this saying? So it's saying that f of n minus 1 is f of n is this. And if you want, you could write it down. In this case, it's pretty simple. So you can write it down as f of n minus 2 plus 2 plus 2. And soon enough, and you can do 3 plus 2 plus 2 plus 2. Soon enough, you will see a pattern that you will have something like f of n minus k plus 2 appearing k times. Right? So is that clear? Okay. So this is just, and what we are doing here is basically unwinding this definition, right? So the definition is kind of this recursive thing, and you're just unwinding this one step at a time. Okay. And you can do this more formally, right? So you can think of this as you want to compute f of n, which is think of it as being the root of a tree. Okay, and this you're saying is f of n minus 1 plus 2. Okay, so this is a the tree node, you can just think of it as combining by plus. And here again you want to do f of n minus 2 plus 2. Okay, and so on. Okay, until you reach f of 1, which has a certain value, and here there's again 2. Okay, so is this tree figure clear? So it's pretty basic. I mean, this is one way of writing out the exact same calculation on the right. Okay, so it's a slightly simpler way to think about it. And so this is what you can generally do for most recurrence relations. Okay, so you write down this, you can expand this as a tree, you can expand the relation as a tree, and you've got to answer two questions. Okay, so first is what is the total, how many steps are there in each layer? What do I mean by steps? Steps are these constants. Okay, so those are the things that eventually get added up, right? So finally here this f of 1 is a constant, and this all the 2's are constants, right? And eventually those are the ones that get added up. Okay, so that's what I call the steps in each layer. Okay, so this is what we've got to figure out. So we've got to figure out how many layers are there, and we just want to, if you have steps of I to be the number of steps in layer I. Okay, so steps are basically sum of all the constants in that layer. Okay, then the total time or the value at top equals sum over I steps of I equals 1 to numbered layers. Okay. So this is just a way of rephrasing the value of f of n. Okay. So just I'm viewing f of n, the computation of f of n as a tree, and I just wrote down what the value at the top is going to be. Okay. So this in this simple example tells you very clearly what's going on, right? So steps of I at the bottom layer. So firstly, how many layers are there in this calculation? Yeah, there's no k at this point, right? So I've gone all the way to n. So there are exactly n minus 1 layers. Okay, so you can think of it as this being the first layer, being the second layer, and this is n minus 1. Okay, because this is f of 1, there will be an f of 2, f of n minus 1. So there's n minus 1 layers. Each layer has 2 in it. Okay, and the last layer has additionally this f of 1, which is a constant. Okay, so you can just use this formula to just basically say it's 2 times n minus 1, which is the number of layers, plus the last layer has this additional f of 1. Okay, so this gives you a clean formula for f of n. Okay. So no matter what f of 1 is, you get some form. Okay, so this is a particularly simple example. So is this example clear to everyone? Okay. So the thing about this method is that it's relatively general. Okay. So you can, if you had any recurrence of some form, you can kind of expand it out like this. Okay. So what are the kind of things that we'll have to figure out? So you have to figure out number of layers, and you have to figure out the steps in each layer, right? So the number of layers, the calculation that it's usually relatively simple. Okay, so in this previous example, it was just the number of layers was roughly n. It was n minus 1. Now sometimes it could be a little bit more tricky. Okay, so sometimes f of n could be dependent on f of n over c. Okay, where c is some constant. Think of c as 2 or something. Okay, so this is what happened in this merge sort example. Right? So one calculation that usually helps if you want to find out the depth of the tree is suppose you drop by a factor of c every step. Okay. So how many steps does it take to reach a constant? Okay. So in particular, if I go from n to n over c square, so on, how many steps are there before I reach 1? Yeah, it turns out to be exactly log n to the base c, and the reason for that is it's easy, right? So suppose you take t steps, okay, and then what you know is that the value you have at the end of t steps is n divided by c to the t, right? Because here it's c, here it's n over c to the 1, here it's n over c to the 2, and so on. Okay, so that's what you have. And you want this to be equal to 1. Okay? And this by definition is basically means that log n is t times log c, or equivalently t is log n by log c. Okay? And log n by log c is essentially log n to the base c. Okay? So it's by definition equal to that. Okay? So this is how you compute the number of steps. Okay? And if you think of c as a constant, this is something that's O of log n. Right? So, okay. Sorry, I forgot that this existed. But one thing to keep in mind is c should always be bigger than or equal to 1. Okay? Bigger than 1, otherwise it won't go down. Right? So if you think of c as 2, then it's exactly log n to the base 2. And one thing to keep in mind is if c is very close to 1, what do you expect the number of steps to be? So, like if you think of c equals 2 versus c equals, oh, it should be 1 plus epsilon, sorry. So it should be, think of this as 1.0001. So suppose c equals 2 versus c equals 1.001. Where do you expect the number of steps to be larger?
C equal to 1.00.
The latter case, right? Because c equals 1.001, because each time you are dividing by something that's really close to 1. So the value is dropping, but at a very slow rate. Okay? So this is just something to keep in mind. And if you do this calculation of log n by log c, you get the same kind of answer. Okay? So the same outcome. Okay? So this is how you compute often the size of a tree. Another thing that is very useful when you are dealing with these kind of problems is the knowledge of how you sum geometric series. Okay. So this is something all of you should have hopefully seen in high school or something. So basically if you have 1 plus x plus something up to x to the k, where x is some number. Okay. Turns out, so what's the answer to this? Does everybody know how to sum such series? Maybe some of you don't remember the answer, but all of you have seen it, right? Okay, so it turns out it is it's x to the k plus 1 minus 1 divided by x minus 1. Okay. So very easy to derive. And it turns out the answer is actually even simpler if you use big O notation. Okay. So think of x as some constant. Okay. So what happens when you try to just use big O notation? So let's think of x equals 1. Okay. So if x equals 1, what's the answer? By the way, for x equals 1, this formula doesn't make sense. So for x equals 1, what happened? What's the summation? Okay. It's k plus 1, right? Okay, so for x equals 1, it's trivial. And for x smaller than 1, okay, so what happens for x smaller than 1? Yeah, it depends on x, of course. It does not depend on k, that's the point. So if x is smaller than 1, this is a geometric series where this ratio actually drops with, so you have 1 plus x squared plus so on, and x is actually smaller than 1. Okay? So even the infinite sum, turns out, converges to a constant in this case. Okay? So yeah, for x less than 1. Okay? So in this case, the overall sum is just a constant. Okay? Because so in particular, the overall sum is even the infinite sum. X to I equals 0 to infinity is something like 1 by 1 minus x, which is finite, right? Because x is smaller than 1, which is positive and finite. Okay? And this is always a constant. So this is always a constant. And if x is bigger than 1, So if x is bigger than 1, what happens? So I claim that only the last term dominates. Okay. So in this case, x to the k minus 1 will be smaller than x to the k, right? Because x is bigger than 1. Okay. X to the k minus 2 is a factor smaller than that, and so on. Okay. So you can, if you really want to reduce it to the previous case, you can write it as x to the k times 1 plus 1 over x plus 1 over x squared plus so on. And this 1 over x is a number that's smaller than 1. Okay, so it's the same calculation as before. Okay, so you can essentially reduce it to the case when x is smaller than 1. Okay, and this part is O of 1. So this whole thing is O of x to the k. Okay, so even if you don't see this exact calculation, you can kind of believe that the leading term dominates, right? Because x is bigger than 1. And so overall you can bound it by some constant times x. Okay. So this is useful to keep in mind. Okay, so these kind of geometric summations behave very easily when you just look in the big O notation. Okay, so alright. So now that we know kind of the basic tools, how you deal with these kind of things. So let's see a slightly more complicated example than before. Okay. So any questions about what I said before? I mean, how you find the depth and how you do some geometric summation. Okay, so I mean, these are all, even if you don't follow the calculations, it's very easy to work them out later. Okay, so it's standard stuff. Okay, so let's look at another slightly different example. So here you have f of n being something in terms of f of n over 2. So it's kind of like merge sort, but imagine 3 calls. Okay, so then the running time would behave like this. And you just have a constant. Okay. So instead of n, you have just a constant. So this is the function. Now how do you analyze this? Okay, so let's. I want to illustrate this tree method a bit more. Okay, so we want to draw a tree, right? So you start off with f of n. Okay, and you know that it's 3 times f of n over 2. So I'm going to draw like 3 things that have n over 2, and you have this constant 41. And each of these guys is going to lead to 3 things. Each one will be like something like f over n over 4. Remember, it's actually f of n over 4 because it's n over 2 divided by 2. And so you have each of these will give rise to 3. Each of these will have a 41 term. Okay. Because that constant is fixed, it's independent of n. Right? Okay, so you have something like this, and so on. Okay. So, and now you have. So here, what do we have? F of what? N by 8. Right? Okay, and okay. Okay, I think I just messed something up, but I'll have to redo this. Okay, but you see the pattern, right? So you have f of n that you want to evaluate, and the first time it's f of n over 2, and you have this constant 41. Then you have f of n by 4. Each of these is divided into essentially 3 things. Okay, and now you have f of n over 8 and so on. So firstly, as I said, you've got to answer 2 questions. Okay, so first is how many layers are there, which is the height of this tree. and we need to figure out the constants in each layer. Okay, and suppose I also tell you something about f of 1. Okay, so it's equal to 5. Okay, so you need some base case information. So, okay, so how many layers are there before you get to 1? Log into the base 2, right? 2 is important because every time you go down by factor of 2, right? Okay, so you have log into the base 2 layers. So this is easy. And let's look at the kth layer from the top. Okay, so this is the k is equal to 1, this is k equals 2 and so on. So what are the constants that are there in the kth layer from the top? So yes, so you always have a bunch of 41s, but how many 41s are there in the kth layer?
41 times k.
Maybe now, since the answers are different, can you? Okay.
I think it's 41 times k minus 1.
Okay, that's 1. Okay, so 41 times k minus 1. But you see, even for k equals 2, right? So this is the layer. You actually have 3 different things.
Okay. So plus 1.
Yeah, so it's
That's squared. 2 to the k.
so an easier thing is yeah. So
there's another 41 that gets added.
is there only one?
It's always multiplying like this.
Yeah. Okay, so if you think about it a little bit, okay, so the number of 41s that get added is exactly the number of f things that are there on the top layer, right? Okay. So for each f you get 141, right? That's the only way you get a 41. Okay. Now, so to answer how many 41s are there in one layer, you've got to answer how many f's are there in the previous layer. Okay. And f's are easier to analyze, right? So in the first layer there is 1 f. In the second layer you know that there are exactly 3 f's. In the next layer, each of the f's gives rise to 3 and so on. Okay. So, yeah, it's 3 to the k. So the number of f's is in layer k is 3 to the k. Okay. So the number of 41s is the number of f's in the previous layer. Okay. So that's 3 to the k minus 1. Okay. So this is. So this is what I wrote here. So you have 3 to the k at depth k. The situation you have is you have 3 to the k copies of this, plus you have 3 to the k minus 1 copies of 41. Okay, so this is the situation. And now what's the total value? So you've got to add up these things, right? Okay, so as I said, you've got to add up all the constants and you have to add up the base case f's. Okay, so let's, as I said, let's say f of 1 equals 5 just for concreteness. So in the bottom layer, what are the constants? So okay, so as I said, the total value is sum over layers I of cost of layer I, and cost of I is total value of constants. And layers, we said that they go from I equals 1 to I equals log n to the base 2. Okay. So we said that there are these many layers, right? Log n to the base 2 layers. So is this thing clear? So this is exactly what I said before. Okay, so to compute the value at the top, you've got to add up the constants in all the layers. Right? Okay, so maybe I will go back to. Okay, so I guess I lost some of this information. But anyway, so right, so generally this is the way we said that we are going to find the value of some recursive cost. Okay, so you add up the constants in all the layers. Okay, And so the value at let's say the first layer is just 41, and then we said that in the kth layer you have 3 to the k minus 1 times 41. Okay. And this is true until the last layer, but in the last layer what else do we have apart from these 41s? Yeah, we have a whole bunch of 5s, right, which is f of 1. Okay. And we know that in that layer you have 3 to the k copies, where k is log n to the base 2. Okay. So we can now do this summation. So let's, for simplicity, let's write, let's say m to be log n to the base 2. Okay. So in the mth layer you have f of 1 times 3 to the m. And you have sum over I equals 1 to m minus 1 of cost of I, and this is 41 times 3 to the I minus 1. Okay, so in layer I there's 3 to the I minus 1 values that are 41. Okay. So is this value here? So this is f of n. Okay. So any question? Yeah.
What is that next step f of 1 times what to the m?
It's 3. Yeah. Okay, because we said that at depth k there are 3 to the k copies of f of n over 2 to the k. Right? So when you set m to be log n to the base 2, 2 to the k is sorry, 2 to the m is actually n. So you have f of 1. Yeah.
Shouldn't the summation go all the way up to n?
Yeah, so I implicitly just broke up that summation into two pieces. So it's 1 to m minus 1 and this is m.
So but even at f1 there's going to be a bunch of 41s.
You're right, exactly. Yeah, good catch. Yeah. So I forgot. Okay. So right, there will be a bunch of 41. So this has to go from 1 to m. Okay. Yeah, and there is this term extra at the last. So any other, yeah.
What does that say to the right of cost of I with the summation?
Oh, it says total value of constants. Yeah, sorry, that constants is not visible. Okay, so this is the calculation. And we saw before that how to do summations of this kind, right? So I told you that if you have a summation of, so this is exactly a geometric summation. So 41 is a constant. Okay? So you can just view this as 41 times this sum over I equals 1 to m, 3 to the I minus 1. And this is just a summation. This is just a geometric summation. Okay? This is like 1 plus 3 squared up to 3 to the m minus 1. Okay? And this one is again f of 1 times 3 to the m. Okay? So what's the overall, if you want to write it in big O notation, what's the overall complexity?
3 to the m.
Yeah, it's exactly 3 to the m, right? Because this one we said before is just O of 3 to the m, because it's sum over 1 x to the I where x is bigger than 1, so the last term dominates. Okay, and so that's O of 3 to the m, and this again is O of 3 to the m. You just have the sum of the two. Okay, so overall this is O of 3 to the m.
Isn't that one 3 to the order of 3 to the power m minus 1?
Yes,
That's
but 3 to the m minus 1 is just 3 to the m divided by 3, and in O notation you just forget about the constants. Okay? Yeah. So
We have three functions
uh-huh.
and we we are dividing n by 2.
Yes.
Why is it not n by 3? Or why is it not 2 functions?
I mean, that's the definition, right? So you are given that f of n equals 3 times f of n over 2. Okay, so that came from some algorithm. Okay, we'll see an algorithm today that where such things come up. I agree, in merge sort there were exactly 2. Okay, but there could be algorithms in which you have 3 calls of size roughly n over 2. Okay, and that's what. So that's how the f is given. Okay, so all this, the tree depends on the f. Then the definition of f has 3 different calls. Okay. So that's a good question. So any other clarification? Yeah.
Can you go back to the next slide and just say again how, keep going, sorry.
Oh, forward.
Yeah,
Okay.
No, back forward, yeah.
Yeah.
So can you just, I'm sorry, I missed it. Can you go over again how, just how you went from the formula there to the big O notation? So we started with f of 1 times 3 to the m, and that was big O.
Yes. So f of 1 is a constant.
Yeah.
Okay. So this is big O of 3 to the m.
Yeah.
Okay. So, and I want to say the second term is also big O of 3 to the m. Okay. And why is that? Because the second term is basically, you can pull that 41 out. Okay. So it's 41 times whatever that is. Now that term, as I said before, is a geometric series. If you think about it, it's just 1 plus 3 squared plus so on until 3 to the m minus 1. Okay, so I just wrote it in summation form, but it's actually just that. And what I said before is that if you have a geometric sum like this, where the term is actually bigger than 1, in this case 3 is bigger than 1, right? So only the last term dominates when you think about it in big O notation. Okay, so that's, and the last term in this case is 3 to the m minus 1, and 3 to the m minus 1 is the same as 3 to the m in big O notation because they just differ by a factor of 3. Okay, so that's why it is that, and that's why that is 3 to the m. You have two terms that are both O of 3 to the m, their sum is also O of 3 to the m. Yeah.
So if instead of it being 3 times f of n over 2, if it was like 0.5 f of n over 2, would that be constant? Because
It would
then
be
the
constant,
geometric
yes.
sum would
Yeah. Because, yes. No, it would be log n because there would be log n different terms. The 41 is always there.
Oh,
So,
so it would be 1 to the...
yeah. So the height of the tree is still log n. Each depth there is 41. Okay, so it's at least 41 log n.
Okay.
Okay, and plus there will be some constant which corresponds to f of 1. So yeah, so this is a good thing. So you guys, when you go back, you can try to think of, oh, what happens if I change that 3 to 5, or if I change that 3 to 1, or something like this. Okay, and then you will rediscover this master theorem. Okay, so it's proved exactly in the same way.
But if it were half, you wouldn't follow the same method. You have to solve it differently. You couldn't use the tree method if it were to be half.
I mean, I can't formally draw the tree, but I could put coefficients. So
And
I
then
will,
use the same.
yeah. So it's, yeah. You said half, not 1. Okay, so for half you're right, it's constant. It's an exercise, you should work out. The 41 will also get divided by half. Okay, so. Alright, so you might want to play with this constant. Alright, so what did we see here? Let's just formally finish this, okay? So we said that for this, the final thing is O of 3 to the m, where m is log n to the base 2. Okay. Now what is it as a function of n itself? Okay, so we'd like to write it cleanly as a function of n, right? So you can plug it in, right? So it's 3 to the log n to the base 2. Okay. So how do you simplify this expression? These are the sort of things that you should just be very comfortable with. You not make mistakes. Okay, so let's just do this. Okay. So one thing to do in all these things is very simple. You should keep track of. You should know two things. Okay. So you should know that a to the b is or any number you want, like 2 to the b times log a to the base 2 or something. So you can always write everything like this. And one thing, and the other thing you should know is 2 to the log n to the base 2. And this is not just true for 2. You can replace 2 with anything. This is equal to n. Okay. So just yeah, these are things which sometimes people do wrong. Okay. So in fact, there's this joke about this. So this really happened. So there was this combinatorialist who was trying to solve some problem with two parameters m and n. Okay. And he was thinking that apparently for a long time that he can obtain an algorithm with running time m to the power of log n. And he wanted to get an algorithm with running time n to the power of log m. And it took him an hour to realize they're both equal. So it's, sometimes you just miss these basic things. Okay, so anyway, so this is yeah. So now you can use these kind of relations to say that this is you can write. Came back. So let's fill this. Okay, so now you can just write this as 2 to the log n to the base 2 times log 3 to the base 2. Right, so I'm just using this formula. I'm thinking of b as being log n to the base 2. Okay, so this is b and a is 3. Okay, so this is what I wrote here, and now I can write this as, now I know that this thing is n. Okay, so I can write this as n to the log 3 to the base. And this, if you calculate, is just something like 1.58. So it turns out this is this. So this is the running time of, I mean, this is the bound you get for f of n. Okay. So is this method clear? So this simplification you can just go back and figure it out if you haven't followed. But this is the general way that you handle recurrences like this. Okay. Okay, so let's, before we move on, let's quickly do this example of merge sort again. Okay, so this will again illustrate. This I will rush through this, but you can easily figure this out too. Okay, so what did we have for merge sort? Right, so you had f of n to be twice f of n over 2 plus n. Right, so there was actually an O of n, but I'm ignoring that constant for now. Okay. So does everyone remember this expression for merge sort? Okay, this is what we saw last time. Okay, so this is what we have, and let's do the same thing, right? So you have 2 times f of n over 2. So you have f of n, and you have f of n by 2, and then you have this n. So n is this additional constant that is there at this iteration. It's by constant I just mean like a fixed term. It's something that you know. Okay. So this is what you have here. Okay, and this step it is f of, yeah, that's why I called it cost, because it's the fixed cost at this time. Okay, so you have each of these f's breaks down into two things again because of the same relation. Okay, so you have f of n over 4, and here what is the extra term you have? What's the constant?
n by 2.
It's n over 2, because each call it's, so you are applying this definition by replacing n by n over 2. Okay, replacing n with n over 2. Okay, so the last thing also changes to n over 2. So you have this, and similarly you have f of n by 4 n by 2. Okay, and you have stuff going on. So again, two questions, right? So what is the depth of this recursion? Log n base 2. So depth is, okay. And the next thing we've got to analyze is how does this depth k step look like? What all terms are there in depth k? Okay. So we've got to analyze these cost terms, right? So we've got to analyze what these additional terms add up to. Okay. So these are the things that contribute to the cost. So let's do this in two steps. So firstly, let's look at depth k. So we know that there are a bunch of f terms. Okay. So what do we have? F of what in depth k? N by 2 to the k, right? So it's in depth k you have bunch of terms of kind n by f of n by 2 to the k, and how many such terms do we have? Sorry, this is 2. We have 2 to the k, right? Because in these things, you figure out it's 2 to the k minus 1, one of these, then you plug in just to see what happens when k equals 2, and you figure out what the answer is. Okay, so this is how you do it, and you have 2 to the k terms like this. Okay, and you also have these extra terms that you have to add up, right? So these are the cost terms that you've actually got to add up. Okay. So how many are there? Yeah, exactly. So you have 2 to the k minus 1 terms, and each one is actually n divided by 2 to the k minus 1. Okay. So this again you can use the same reasoning, right? Goes down geometrically. For k equals 1, it's n. So it's it's n over 2 to the k minus 1, and there are exactly these many terms. Okay. So this also you'll figure out after a bit of thought. So these things, if you think about it, they add up to exactly n, right? Because there are these many terms, each of which is this. So that's why they add up to n. So that's a nice property to have, right? So we are saying that these cost terms in every level, they add up to exactly n. And this is true for all these layers. So the bottom level usually is a little bit more special. So what does the bottom level have? So it has a bunch of f of 1 terms. We know that, let's think of f of 1 as a constant. Okay, so in the merge sort example, we just return the array, so it's just 1. Okay, so f of 1 is 1. And you have 2 to the k terms, and 2 to the k in the last case is exactly n. Okay, so these add up to n. So in the last level, you have n coming from the f of 1 terms plus n otherwise. Every other level you have exactly n. Okay. So the calculation in this case is very simple, right? So it's you have sum over I cost of I going from 1 to log n to the base 2. and plus this for the base case, you get an extra n because of the f terms. Okay. So that's this, and this is each cost of I is n. So this is it's n times the number of levels. So this is n log n to the base 2 plus n. So I'll just write it as O of log n times log n. Okay. So this is how you get this n log n bound for merge sort. Okay. All right.
Just because there's an N on the top.
So any other questions about this? Okay, good.
Sir,
Yeah.
could you tell me what the extra, can you re-explain the extra n?
The extra n came from these f of 1 terms. So this has been happening even earlier, right? So you have
Right.
a bunch of, so you have this cost of I, which is these extra terms, which is the cost terms in each layer.
Right.
And then you have this base case terms, which are the f of 1 term. And here there happen to be exactly n such terms, and they actually give rise to that. Each of them is 1, so that's the extra n. So yeah.
So just so I'm clear, we start counting the layers from their root, and then we count up as we go down, right? That's how the case work?
The k goes from top to bottom because
So when we say the previous layer, we go up a layer. Closer to the root.
Yes, yeah. Yeah, usually this is what we do for a tree. You start counting the layers from the top, and the root is the 0th layer, and then you have the first layer and so on. Alright, so let's, so this is the analysis for merge sort. Okay, so this is what shows, this is the full analysis now for merge sort. Okay, so we saw that, the algorithm proved its correctness, we bounded the running time as a recurrence, and we solved this recurrence. Okay. Alright, so this is supposed to give you a gist of how you solve recurrences in general. There will be a bunch of homework questions where we will see, some other examples. Okay. So let's now move on to something else. So this is an example that I started off with last time. Okay. So this is an example where, as I said, it's hard to see how divide and conquer can help you. Okay. So let's see how you will do this. So let's look at multiplying two n-digit integers. Okay. So I wrote two integers here. Okay. So these, imagine they are like n digits. Okay. So you have two of them, and you want to multiply them. So all of us know this high school algorithm, right? So it is, you multiply digit by digit, okay, and then you stack them up in this staggered way, and then you add these things, right? So hopefully all of you have seen this. Okay, so let's quickly see how long you take to multiply two n-digit numbers using this algorithm. Okay. So what are you doing? Firstly, you got to build these things. So each one, how long does it take to build each one?
N plus 1.
N or O of n, right? So it takes roughly O of n time to build each of these numbers, and you do n of them, okay? Because the number of things you do depends on the number of things in this bottom thing, which we assume is also n. Okay, so you have two n-digit numbers. Okay. So we have n things, each of O of n. So building this representation itself takes O of n squared time. Building these partial things takes O of n squared time. And now we've got to do some adding. Right? So how long does the adding take? This, each digit is it's O of n, right? Because, okay, so initially you're a little bit lucky, but once you start going a little bit further in, you will start seeing roughly n things. okay, like n over 2 or something like that. So it's easy to see that each addition could take roughly n, and therefore the overall thing is like n squared. Okay. And this happens to be the best you can do using this algorithm. Okay. So it's O of n squared. Okay. And the question is, can you do any better? Okay. And this apparently, I mean, it took a while to come by. Okay? So for a long time, people didn't know how exactly to do better than this. Apparently, Gauss did in the 1800s, but he never wrote it up, so nobody really knew about it. And it was posed as a challenge in the 1950s about, can you do better than n squared? Okay. So the same kind of questions people have thought about for matrices. Like the usual algorithm that you all know of would take n cubed time. Okay, so can you do better than n cubed? So that's so these are questions that people have thought about. Okay, so this is the kind of a question we usually think about in algorithms. Okay, so we come up with some algorithm and we wonder whether you can do better asymptotically. Okay, so in this case, it turns out there is a clever way to do this better than n squared. Okay, and that's what we will see now. Okay, and rather surprisingly, the answer is to do divide and conquer. Okay, so let's see. Okay. So now that we saw some examples and we are experts in this, let's try to see how you would do divide and conquer. Okay. So you've got two n-digit numbers that you want to multiply, right? So let's write them out in like nice block format. This is x and this is y. Okay. And so what do we do in divide and conquer? We try to break up the problem into two pieces, right? And hope that we can solve these pieces and put the answers together. We can try to do this. So let's say you break this up x into two pieces. I will call these a and b, okay, and y into two pieces which I will call c and d. Okay, and suppose I break at roughly n over 2. Okay. All right. So how do I write this? Okay. So if I want to use divide and conquer, and I call this part A and this part B. So firstly, how do I write x in terms of A and B? So I want to write x as some function of A and B. Yeah.
Is it decimal? Are they decimal?
Let's think decimal.
So then you just left shift a by the.
Yeah. So first you take A, okay, and you shift A by the number of digits you have in B, okay, and that's in this case it's 10 to the n by 2, and then you add B. So you can think of it as you take A, put n over 2 zeros, then you add B to it, then you'll get exactly x. Okay. So this is x. You can do the same for y. C times 10 to the n by 2 plus b. Okay. So is this representation clear? So this is just basic arithmetic. You can think about it for a bit and you can access that. So that's fine. Okay. So now you have an expression for x times y. So this is you can multiply these two expressions and you get AC times 10 to the n plus AD plus BC times 10 to the n by 2 plus B. Okay, just multiplying this out in hope I don't make any mistakes, because here mistakes are expensive, as you'll see. so this is how I wrote this, right?
AC and B come from the previous in the table. If you write an algorithm
So yeah, so let's see. So firstly, you know that if you find these products, right? So AC, AD, BC, BD. Okay? So each of them is a product of two n over 2 digit numbers. Okay? Because A is an n by 2 digit number, C is all of them are n by 2 digit numbers. Okay? So A times C, A times D, B, C, all of these are n by 2 digit numbers. So if you knew all of these things, then you can find x times y, right? Because you can find A times C, shift it by n, and then you find AD, and then you add it to BC, so on. And you can do you basically need 4 recursive calls to find out these 4 things. And then you need linear time to add them up. Okay? So this gives this running time of, this should be capital N. Yeah, this gives this running time of T of n being 4 times T of n over 2 plus O of n. Okay? So this is clean recursion. Okay, so you do each of these in T of n over 2 time, and this is what you do. And so what does this give you? So you can try to solve this. So you can draw the same tree and so on. So I'll just rush through this. So you have 4 leaves, T of n over 2, and you have O of n. So the problem you will see is that the depth will be the same. The depth will be log n to the base 2. Okay. And but you will get, after the kth level, you will actually have 4 to the k different f terms. Okay. So in this bottom level of the tree, you will observe that you have 4 to the m, where m is again log n to the base 2, 4 to the m times f of 1, okay, or t of 1, okay, plus something. And this itself is too bad, okay, because if you again plug in what m is,
N square.
yeah, it's n squared, because you get 4 to the log n to the base 2, and this is basically 2 to the, or you can think of it as n to the log 4 to the base 2, which is exactly 2. Okay, so 4 is 2 squared. So yeah, if you don't follow this, don't worry. So this turns out to be n squared. Okay, and this is bad, right? Because what you're saying is, okay, you try to do divide and conquer, you have these terms, and you again got an n squared thing. Okay. So this is not great. So how do we improve this? So the main observation, so when you try to design algorithms, this is what you should be doing. Okay, so you come up with some algorithm, and you analyze its running time, you feel it's too bad. You've got to look at all the steps and see, is this step really necessary? Okay, so let's see what's going on here, right? So you have this x times y, and you wrote it as AC times this plus AD plus BC times this. Right? So here, to compute these things, you need AC. Okay, you need the sum of AD plus BC, and you need BD. Okay. Now the point is, you don't need AD and BC individually. Okay, so as long as you can somehow obtain their sum, you are in good shape. Okay, so that's the thing we want to analyze. Okay, so and in particular, suppose you computed AC and you computed BD. Okay, you've already invested some computation. Can you use that knowledge to find AD plus BC faster? Okay, so that's the key idea behind this algorithm. Okay, so you compute AC and BD using a recursive call, and the last one you don't use 2 recursive calls. Hope is maybe you can do it with just 1. Okay, and that's what we'll show you can do. Okay, and the tricky observation here is, so let's say you compute A minus C sorry, A minus B times C minus D. Okay. I think you can even do plus. Okay, so let's do plus. It's you don't want to deal with negative numbers and so forth. Okay, so let's do plus. For some reason, people usually write it with minus. So what is A plus B times C plus D? So it's AC plus BD plus AD plus BC, right? Note that AD plus BC is exactly the kind of term we want. Okay. So this is great. Okay. And we said before that you already found AC and BD. Okay, so these two you've already just computed. Okay. And now all we are interested in is AD plus BC. Okay. So what this means is that if you computed this product and you subtracted AC and BD, okay, then you get exactly this this extra term that you want. Okay. And so does everybody see this? So you essentially have reduced it to only 3 multiplications. Okay, so A plus B is a maybe n by 2 plus 1 digit number. C plus D is also an n by 2 plus 1 digit number. So you essentially reduced it to 3 different computations of roughly n over 2. Okay, so and then you have these addition steps which again take linear time. Okay, so it's slightly higher linear time now, but it's still linear time. Okay, so is this trick clear? So basically the main observation is you've got to get this, you've got to get this, and you have to get this. So these are 3 terms that you want to get, and the point is, do you really need 4 multiplications to get these 3 terms? Okay, and the answer is you don't. You can actually do it with 3 multiplications, and the idea is you do the first and the last, and then you do this trick. You multiply these 2 numbers instead, subtract them off to get the term. So this is the idea. And one thing we used here is that additions are cheaper than multiplication. So that's one of the things we used, because found this and you subtracted off AC and B, and those only take linear. Okay. So this is the idea behind the algorithm, and you can formalize this. Okay. So this was first formally invented by Karasupa. And the way he did it is, and this is exactly what we said before. So we said plus, so let's do plus. Okay. So these are the steps in the algorithm, right? So you have multiply x and y. You divide them into blocks of size n over 2. X is A and B, and y is C and D. You multiply these two, multiply BD, multiply these two, and then you find AD plus BC and return that. Okay, so these are just the formal steps in the algorithm. Okay, and the answer is exactly that 10 to the n times AC plus whatever. So let's analyze the running time of this. Okay, so what time does this take? So suppose this is T of n. Okay. So T of n is the running time of this, let's say. Then this is multiplication of 2 n over 2 digit numbers, right? So it's T of n by 2. Same for this, and same for this. You have to be a little bit careful. It's n by 2 plus 1. Okay. But it's roughly the same. You'll realize that the induction works out correctly. And how long does this take? So first you have to find this AD plus BC, and then you have to return the answer. Yeah, this takes n because to find AD plus BC, you took something that you already found, which is this multiplication. You did some subtraction. Okay. So, and that is linear time. and doing this 10 to the n times AC plus whatever to find the answer is also linear. So this is turns out to be O of n, and this means that you get this recurrence relation. You get T of n is 3 times T of n over 2 plus O of n. Okay, so this is what you get. And yeah, so this I won't solve it, but you can do the exact same kind of analysis that we did before. Okay. So if you remember, we did something very similar to this, but we did 41 here. Okay. So turns out it doesn't matter whether you had n or 41. Okay. So I was planning on doing this, but I probably won't. Okay. So you can do the same kind of analysis. You break it up into two, and then you have an n. Okay, in this again you have 3. Okay, and you'll see that the number of f terms you get at the end will be 3 to the m. The depth is again log n to the base 2, which we call n, and then you basically get O of 3 to the m, and this turns out to be n to the 2, and this is again O of n to the. Okay, so I'm not doing this in detail because this is roughly what we did before. Okay, so we in fact had the same T of n being 3 times T of n over 2, plus we had a constant before. Okay, but it turns out even if it's n, those n terms actually add up to something smaller than usual. Okay, so it's not you can think of this as just an informal exercise. This is also there in the notes, so I'm not going to do this in detail. But is the idea behind the recurrence clear? So basically the thing was, you went from something where you had a 4 out here to a 3 out here. Okay, and that gives the asymptotic improvement. Okay, so this is what is called Karatsuba's algorithm. And yeah, so one question you can ask is, okay, so this is a pretty clever algorithm, and are there faster algorithms for multiplying two n-digit numbers? Okay. So when you design algorithms, right? So one thing that should strike you is, you know, this n to the 1.58 something. It looks like the outcome of a trick, right? This can't be the true answer. Okay, so it's just a moral thing, right? So it's you don't expect it to be the true answer. You expect that maybe you can do something better. Okay, so it turns out you can, and here there's an algorithm that is actually based on fast Fourier transform. So it's not very difficult, but it's a little bit tricky. So I won't cover it in this class, but you can look it up in the notes. Okay. So how many of you know what fast Fourier transform is? Oh, okay, good chunk. So I guess all the E people would definitely know. And point is, how the hell does it apply to this setting? So it turns out there is a very clever way of doing it, and I won't get into it, but it's clever. And it gives runtime of roughly n times log squared n. So it's almost linear. Okay, so it's n plus some log factors. Okay. So I think people could also improve this to n log n log log n or something like this. So there's actually a whole army of people who just study how quickly you can do multiplication. Okay, so that's and this is I guess the best known. There are some recent improvements in some special cases and so forth. And so I guess the main motivating force for this class of researchers is not that you want to do it in n times, I don't know, something square root log n or something, but question is you want to get at the limit of these problems. Okay, so you want to see how quickly you can solve this problem. And in some sense, having matching lower and upper bounds is what is the goal of complexity theory. Okay, so this is really the motivating field for them. So can we prove that, for instance, there are no algorithms that can do better than n log n? So that's what is conjectured, but nobody knows how to prove these sort of things. So, and this is this whole area called complexity theory, where the goal is to show things like this, okay, among other things. So, all right. So we have maybe a couple more minutes, right? Or no? Okay. So then, let's break and next class we'll see what's called dynamic programming.